Hey guys, welcome to week number 5 of the Ace Your IB Math Exams in 10 weeks challenge. This is week number 5. If you do not know me, I'm Bruno, the IB Math teacher. I've worked as the head of the mathematics department in one of the most prestigious IB schools in Brazil, also the HL math teacher, and I'm also an IB math examiner. And for this May 2026 cohort, I've decided to launch you can call it a course or a challenge, the Ace Your IB Math Exams in 10 weeks challenge, where in each week we tackle one question from each one of the 5 different IB math topics: number and algebra, functions, trig, statistics, and calculus, with challenging IB math questions as a way to mimic what you're going to face a few weeks from now. You can find all materials the past few weeks, the YouTube videos and the PDFs in the description of this video right here. Everything is for free. And I'll also want to encourage you to share that with your colleagues so you guys can study together, given that studying together is much more fun than studying by yourself. So let's get to it. Let's get through week number 5 of the Ace Your IB Math Exams in 10 weeks. All right, so let's get to it. Exercise number 1. We have a geometric sequence with the following formula for its sum. The sum of the first n terms equal to negative k to the power of n plus 3 to the power of n over 3 to the power of n. And we know that k is a positive number. So we need to find firstly the expression for r, which is the common ratio of this geometric sequence. And in order to do so, we can find 2 consecutive terms, which it's easier if we find the first one and the second one and calculate their ratio. So u2 over u1. Now, S1 and U1, they're the same. The sum of the first terms, the first term is just U1, right? Now, the sum of the first 2 terms, that's going to be U1 plus U2. So when we get to S2, when we calculate S2, we need to make sure that we understand that we have to subtract U1 from it to get U2, but we're going to get there. So as I was mentioning, S1 is the same as U1, which is negative k to the first power plus 3 to the first power over 3 to the first power. So this is our U1. Now S2, which is the sum of the first 2 terms, U2 plus U1 or U1 plus U2, that's equal to negative k squared plus 9 over 9. Now we need to find U2 to find the ratio of this geometric sequence. So let's subtract from S2 or U1, which was calculated before. So we know that U1 is negative k plus 3 over 3. Therefore, our U2, and let me move this down because I ran out of space, it is equal to negative k squared plus 9 over 9 minus negative k plus 3 over 3. We can use 9 as a common denominator. So negative k squared plus 9 plus 3k minus 9. So we have as our U2, not as our ratio, but as our U2, negative k squared plus 3k over 9. Therefore, the ratio, which is U2 over U1, it is equal to this U2 over U1, which we found in the beginning. So we get negative k squared plus 3k over 9, and we multiply by the reciprocal of the fraction in the bottom. And by the way, you can factor out a k here and simplify these and find 3k over 9, which is k over 3, as the final answer. All right, so now that we have our k, or actually our ratio, we can find the values for k for which the sum to infinity exists. We know that for the sum to infinity to exist, the ratio needs to be in between -1 and 1. And what that means is that -1 has to be less than k over 3, which is less than 1. Therefore, if you multiply everything by 3, you should get -3 less than k, which is less than 3. Now, it was given by the exercise that k is a positive number. Therefore, the actual interval is from 0 to 3, given that k has to be positive. And then we have question B2I. Find the sum to infinity for those values of k, which looks weird because you would imagine maybe that for different values of k would give you different sums to infinity. But let's see if that's actually the case. This is a formula which is present in your formula booklet. It is equal to U1 over 1 minus R. And we know for this specific case that our U1 is negative k plus 3 over 3. And we have our ratio as k over 3, which means that in the denominator we have 3 minus k over 3. And in the numerator, if you rearrange k and 3, you get 3 minus k over 3 as well. Therefore, the sum, it is equal to 1. And it doesn't depend on the value of k. And by the way, this is where a geometric sequence presents a sum which is finite, even if it has infinite terms. So the radius of convergence, or the ratio of this geometric sequence, it has to be in between -1 and 1, which is what we used before. This is just another way of saying the same thing. In exercise number 2, we have a quadratic expression, one which we could turn into a function just so we can analyze what happens to this quadratic when it's not represented in the standard form, which is the form that's given, but actually in vertex form, which is the x minus p squared plus q. So let's assume that g of x is equal to x squared minus 6x plus 14. And this is the standard form of this quadratic. Now, in order to convert this to vertex form, we can either, number 1, complete the square, which is fast, or number 2, extract the coordinates of the vertex, which, by the way, in this case are p comma q, by remembering that the x coordinate of the vertex is equal to -b over 2a, and the y coordinates of a vertex is the function when evaluated at xv. And by the way, what is a, b, and c here? A is equal to 1. These are the coefficients of this quadratic. B is equal to -6, and c is equal to 14. Now, when you do -b over 2a, you get -6, meaning +6 over 2 times 1. So xv, which is being represented as p, is equal to 3. So we already have part of this vertex form. How do we get the q, which is outside this set of parentheses? We need to plug in 3 into the quadratic, meaning 3 squared minus 6 times 3 plus 14, which is equal to 5. Now do notice that is being represented as q over here. So that's how we write x squared minus 6x plus 14 as x minus p squared plus q. In other words, we just completed the square. Now for question B, we have something different, a different function, which is 1 over that quadratic, or sorry, 2 over that quadratic, meaning 2 over f of x, 2 over g of x, that is our f of x. You can represent f of x as 2 over the quadratic, or as I mentioned, 2 over g of x, given that we're calling the quadratic g of x. Now, it is important at this point to go back to exercise A and to analyze the quadratic, the curve that we got. If you were to plot it, given that the x value of the vertex is 3 and the y value is 5, you could represent it like this, and we know it's concave up because the coefficient A is positive. Therefore, we have a minimum point, which is the vertex right here. Now, if we're talking about a function which is 2 over this same quadratic, x squared minus 6x plus 14, what gives us the maximum result for this is whatever gives us the minimum result for this. And why is that? If you picture this as a gigantic number, 2 over a big number is going to be small. However, if x squared minus 6x plus 14 takes the place of a small number, then 2 over a small number becomes a bigger one. Now, let me show you with 2 different examples. Let's say that you're talking about f of 0, which is 2 over g of 0, or 2 over 0 squared minus 6 times 0 plus 14. Now, x equals 0 is right here, and the y value for this quadratic, which was found in question A, this is equal to 14, just like we can see it right here. Now, over here, we get 2 over 14, which is 1 over 7, as the result. We would get a much bigger number if we used the smallest one that we could find in this quadratic, which is the vertex. For x equals 3, the y value is 5, which means that f of 3, which by the way will be the maximum of f of x, it is equal to 2 over 3 squared minus 6 times 3 plus 14, which we know is equal to 5. So this is equal to 2 over 5. Therefore, the coordinates of the maximum point on the graph of f of x is 3, 2 over 5. If you actually plot this graph, you see that f of x does not produce any larger result than 2 over 5, aka 0.4. And there you go. This is exercise number 2. We're almost halfway there. Exercise number 3, one that involves trick. Edna loves going to the beach and finds it relaxing to stand in wavy water. We can see that the water is rising and lowering as time goes by. And this is a very typical application of a trig function, given that it oscillates, it mimics a periodic behavior. And trig models, they have the following shape. We have a constant a, which represents the amplitude. We have a constant b, which represents the period in quotes, because the period is actually 2 pi over that constant. Which, by the way, if you're wondering, it also means that b is 2 pi over the period. So these are the same. We can also see c over here, which represents a horizontal shift of the graph of this function, and this d, which is the vertical shift, which also represents the principal axis. Now let's extract some information from the exercise. We know, for example, that whatever happens again after 3 seconds, which means that the period is 3, which allows us to calculate b. So b is 2 pi over 3, which, by the way, is question A. Now, before finding the other constants, let's represent this graph. We have this person's feet, and this is my attempt of drawing feet. This is the person's knee, and we know that after 1.1 second, and then again every 3 seconds, meaning the next one will be at 4.1, the level of the water will be at the person's knee, which is 55 centimeters from the ocean's floor. We also know that the ankles are 12 centimeters from the ocean floor. So this is what the curve will look like. In order to find this principal axis, which is the vertical shift, we do max plus min over 2, meaning max plus min height, which in this case gives us 33.5. And now the amplitude can be found by calculating max minus min over 2. And we know that A is positive. It was given by the exercise. That piece of information, was given by the exercise. So we have 55 minus 12 over 2, which is 21.5. So up to now, our model looks like this. D of t is equal to 21.5 cosine of 2 pi over 3, t plus c, plus 33.5. Now, given that at 1.1 seconds, the height is 55, given that the water is touching her knees, you can use the numeric solver with this function and this point right here, which means that you're going to throw in the point 1.1 comma 55 into the function. So 55 equals 21.5 cosine of 2 pi over 3, 1.1 plus c, which you're going to need to replace it by x in your calculator, plus 33.5. When you plug it into the numeric solver, make sure that your interval is from 0 to a big positive number. Don't use negative numbers in your interval because the question is asking for the smallest positive value of c. And when you do so, you should get c equal to 1.9. Now, one question that you might have is, how would I do that if this was a paper 1 question, which could be the case for this exercise C? Well, you would need to solve this algebraically. You would subtract both sides by 33.5 and then divide both sides by 21.5, which means that you would get 1 equals cos of 2 pi over 3, 1.1 plus c. And then you would need to think, what is the arc that gives you a cosine of 1? And there are infinite answers for that question. There is, for example, 0 or 2 pi or negative 2 pi and so on and so forth. Now you should divide everything by 2 pi in order to get rid of this. So you get negative 1, 0, 1, all the way up to infinity equals 1 over 3, 1.1 plus c. Then you multiply everything by 3, which gives you these results. And then you subtract 1.1 from each one of these options, each one of these solutions, meaning you would get negative 4.1, negative 1.1, and then the first solution, which is positive, which is the correct one. Therefore, the first positive number is 1.9. So this is much harder than using the numeric solver, of course. Now for question D, there's no way to do this without the calculator. You need to find the amount of time within the first 15 seconds, meaning your interval will be much bigger where the water is above 40. So graphing the function and graphing the line y equals 40, you should find this interval by calculating the intersection between the line and the curve. And whatever you get as the x values here, which are 1.70 and 0.497, you find the difference between the two, which is the interval, 1.206 ... And you're going to multiply that by 5, given that there are 5 of these intervals, until you get to 15. So you have 5 times 1.206, you get approximately 6.03 seconds. All right, so a nice probability question, one that involves a little game. These are usually the trickiest probability questions, the ones that involve multiple items in the same question. So let's see what's happening in this scenario here. So we have a bag which contains n marbles. 2 of these marbles, they're blue, 3 are red, and all the others, they're all black. We don't know how many exactly, but they're all black. Lada plays a game in which she randomly draws marbles out of the bag, one after another without replacement. This is very important. Whenever she gets a red marble, the game is over, which means that if we're trying to find the probability in terms of n that the game will end on her first draw, well, on her first draw, she needs to draw a red marble. How many red marbles do we have? It's 3. So we have 3 red, 2 blue, and some which are black. We're going to state as a function of n how many black ones we have in a minute. However, the probability that she loses on the first draw is 3 out of the total, which is n. Now, how many black marbles do we have? If we have n in total, then this is n minus 5. Notice that if you add all of these numbers, you get n. Now, what is the probability in terms of n that the game will end on the third draw? That means that on the first and on the second, she cannot draw a red marble, which means, and considering the fact that there's no replacement, that she has n minus 3 out of n options in the first draw. And where does that come from? That comes from the sum of n minus 5 and 2, which means that she drew a black or a blue one out of this bag. Now on the second draw, there are n minus 1 options because one of them is not being replaced, which could be a blue or a black. And now we have n minus 4 options, so 1 option less. And on the third, she needs to draw one of the red ones out of n minus 2. We have n minus 2 in total now, that we have 6 black marbles. And Lada is playing the following game. She draws 3 marbles. For each blue marble drawn, she earns 15 bucks. For each black one, she earns 6. And if she draws a red marble, then the game stops. Now, in this case, the probability of losing in her first draw is 3 out of the total, which is 11 now. So the probability of losing on the first is 3 out of 11, which we can represent in this table right here, which we're going to end up filling completely in the next few questions. Now, for question 2i, we need to show that the probability of winning $21 is 4 over 55. So we're verifying this result, which is already on the table. And a slight hint was given here, which is for her to win $21, she needs to draw a blue and a black, or a black and then a blue. And for the third marble in each one of these cases, well, it has to be a red one. So she loses and ends up with only $21. And by the way, that's the prize money. That's not exactly the profit because she still will pay to play the game, but that's only for question number 4. Now let's consider these two scenarios. Blue, black, and red, which means 2 out of 11, then 6 out of 10, which is the black one. We have 1 marble less, so instead of 11, we have 10 now. And then 3 out of 9. Or, and or in probability means plus, black, blue, and then red, which is 6 out of 11, 2 out of 10, and 3 out of 9, which is in fact 4 out of 55. All right, so let's now complete the table with all the probabilities and the prizes. It's easier to start with the prizes because, well, it's just adding the prizes for each individual marble. So for this case, for example, we have 2 blue and 1 black, which means 15 plus 15 plus 6, which is 36. Then we have 2 blue and 1 red. The red represents the person losing, which means only $30. And then we can continue from there. So 2 black and a blue, which is 27. Then we have 3 black, and so on and so forth. Now, to find the probabilities, I'm going to start with this one specifically just because I want to illustrate the scenario completely so there's no misconception or misunderstanding of what this represents. We have 2 black and 1 blue, which can happen in any order. So 2 black and 1 blue, they are 6 over 11, that's the first black, 5 over 10, that's the second one, and 1 blue, which is 2 out of 9. And there are 3 ways of arranging that, which is black, black, blue, black, blue, black, and blue, black, black. So multiplied by 3, which means 2 over 11. And that doesn't happen, for example, in this case. Because in this case, if we try to put or place the red before, well, the person loses, and this situation does not make sense anymore. The losing portion, which means extracting a red marble, has to be the last one. And also switching the order of the blues, well, it doesn't change anything. So we have the first blue, the second blue, and then the third one as a red one, which is 1 over 165. Now over here we have 3 black, and we cannot do anything with the order here, so 4 over 33. Then we have a blue and a red, 3 over 55, 2 black and 1 red, 1 over 11, and a black and a red, which is 9 over 55. Now let's jump to the last question. Given that Lara pays $12 to play, find her expected profit and explain its meaning. Now, this is the price for each scenario, which does not represent the profit. The profit is for each one of these cases, whatever these are, minus $12, which means over here, 24, and then 18, 15, 9, 6, 3, 0, negative 6, and negative 12, which means that the expected profit, which is a product between the profits and their probabilities, it is equal to 24 times 2 over 55 plus 18 times 1 over 65, 165, plus all the way down to negative 6 times 9 over 55 plus negative 12 times 3 over 11. And the expected profit is positive $1, which means that in average, each person that's playing is expected to win $1. All right, so lastly, a differential equations question, one that we're going to start solving using Euler's method. That means using the calculator, and then we're going to use some sort of method. We need to decide which one works in order to solve this algebraically. So let's start with Euler's method first. Consider the following differential equation. We know that when this differential equation is solved, we get a function with respect to x, and this function crosses the point 1 comma e cubed, and that is given over here. Now we're going to apply Euler's method using h equal to 0.1. And that will allow us to go from 1 to 1.5, which is right here, in 5 steps. From 1 to 1.1 to 1.2 and so on and so forth until we get to 1.5. Now, how can we use the calculator to do this? You got to be careful when you're placing where you're inputting the differential equation, because it's very easy to make a typo. You need to rewrite this dy dx in this way. You need to write it isolating it on the left hand side. So what do we have? We have the step size equal to 0.1. We have the starting x value 1 or at 1, and we have the starting y value at e cubed. Let's consider this iteration 0. We're going to go all the way to iteration number 5. Now we have xn plus 1, which is the next x as the previous one plus the step size. And this is something that you can fill in the table already. You don't need a calculator for that. But given that for y we need that result, we're just going to input everything in the calculator. And yn plus 1 equal to yn plus the step size times dy dx. And this is a much better way of viewing this formula, evaluated at xn yn. Now I encourage you to learn to do this, to go through this process using your calculator. I'm going to use a TI-84. However, the methods for doing this when using the TI-84 and the Inspire and the Casio, they are different. So do make sure that you know how to apply this with your calculator. So for the TI, first of all, we're going to go to the sequential mode. And then in our y equals, we're going to set our n min to 0. And knowing that u represents x and v represents y in this calculator, our initial x is 1 and the initial v is e cubed. Now the formula for x is u n minus 1, which represents the previous x, plus the step size, which is 0.1. Now be careful when you're writing the expression for y, given that at some point we're going to need to input dy dx, which is a huge expression. So we have second v of n minus 1, so the previous y, plus 0.1 times our dy dx. And inside, we're going to insert the formula for dy dx. Now, after inserting this gigantic expression, which is a challenge in itself, you should second table it, which means that by inputting the data in our table, when x is equal to 1.5, we get 98.725. So this is our approximation for y of 1.5. So the value of the function when x is equal to 1.5. We're going to solve it algebraically to see if we actually got a reasonable solution. All right, so let's solve this algebraically. We have a y over x here, which points towards using or facing this as a homogeneous differential equation, but let's see if that's actually the case. We can definitely rewrite this as y over x times 1 plus ln of y minus ln of x. And this can be rewritten as ln of y over x. So indeed, this looks like a homogeneous one in which we substitute y for v times x and dy dx for v plus x dv dx, which means that we get v plus x dv dx equal to v, which is y over x, times 1 plus ln of y over x, meaning ln of v. So we have v plus x dv dx equals v plus v times ln of v. We can cancel out the v's and rewrite the left-hand side as dv over v ln of v and the right-hand side as 1 over x dx, which allows us to integrate both sides. Over here we have a substitution where u is ln of v and du is 1 over v dv. Therefore, on the left-hand side, we have 1 over u du. And on the right-hand side, we have the integral of 1 over x, which is ln of x plus c. We can go ahead and place the constant already. So the integral of 1 over u, ln of the absolute value of u, equals ln of x plus c. By replacing back the u, we have ln of v equal to ln of x plus c, which means that e to the power of ln of x plus c is equal to ln of v, which can be rewritten as e to the ln of x times e to the c. So we have ln of v equal to positive and negative e to the ln of the absolute value of x times e to the c. This equal to the absolute value of x. And we can place back the y over x that we had before our substitution. So we can find this constant here. So finding c, we get ln of the y-coordinates of the point given over the x-coordinates of the same point equals positive and negative absolute value of 1 times e to the c. So e to the c can be replaced by ln of e cubed, which by the way is 3 ln of e, which is just 3, which ultimately gives us ln of y over x equal to x times 3. And by the way, given that we already considered the two possible cases, we can remove this absolute value as well. So y over x is e to the 3x, which means that y is x e to the 3x. Now let's see if we got a good approximation. What is y of 1.5? We need the calculator for this. Y of 1.5 is 1.5 times e to the 3 times 1.5, which is approximately 135. By the way, this is the actual result. Therefore, the percentage error is 135 minus 98,725. Don't forget to use all the digits here. Over 135 times 100, which gives us approximately 26.9%. So the approximation wasn't so good. Now that's it, a very long and demanding exercise in differential equations. All right, so that's it for week number 5 of the ACE Your IB Math exams in 10 weeks. I'll see you on the next one. If you've missed any day, any PDF, any YouTube video, you can find all of those in the description of this video. I'll see you on the next one.